Okay, in this PowerPoint, we're going to go over the renewable energy sources. That includes solar energy, wind energy, wave energy, and the other one, hydroelectric. Okay, as a quick review, don't forget that power is equal to work over time, or in other words, work is how much your energy changes, so change in energy per unit time. We're going to use that a lot in this PowerPoint. Next on our list is wind power. What are some of the energy transformations with wind power? Remember, so wind goes through the turbine, through this windmill, and it's going to spin it, right? But the energy before it was wind was something else. How did it turn into wind energy? What allows wind to move? If you'll remember right, the sun is, or the wind is is caused by the fact that there are hot spots and cold spots on the earth, and air rushes from the hot spots over to the cold spots, and what creates the hot spots and cold spots is the sun. So it actually starts as solar energy, then turns to kinetic energy of the air, which spins the turbine, okay, and kinetic energy of the fan blades, and then which spins the generator, which creates electrical energy. Okay, so if we make a Sankey diagram of this, it'll be solar energy turns into kinetic energy of the air, which spins the turbine, but again, not all of the energy goes into spinning the turbine, because some of the energy is the air is probably most likely still moving, so that's our degraded energy, and then the spinning turbine energy turns into electrical energy, and you could lose energy here in this process as well, because the generators, of course, are also not 100% efficient, so we should probably actually have some lost energy there as well. Okay, so one thing you should know, while hydroelectric dams are very efficient, up to 70% efficient. Most wind turbines aren't that efficient. The general efficiency can be anywhere from 25% to maybe 40% if you're really lucky, but it's usually lower, right around the 25% area. Optimal wind speeds. There are optimal wind speeds that you need to be aware of this. The fact that if you go too fast, right, then those fan blades are just going to spin and rip right off, and you can even YouTube some videos and see that. So you don't want it to go fast, but you also don't want it to go too slow, because you're not going to generate very much energy. So there is an optimal wind speed for maximum power production, and which makes you can get the most energy out of that wind, and those optimal speeds are anywhere between 6 to 14 meters per second. That's how fast you want the wind to go, 6 to 14 meters per second. So there's only certain areas that you really can do these wind turbines. So some pros and cons. It's pretty much free. Again, you get it built, and then it just produces that electricity. Also, it's inexhaustible. There's always going to be wind. Now, there will be some days with it and some days without it, but it'll always come back. Also, it's clean, meaning no carbon emissions. It's ideal for remote island locations like Hawaii and places where there's a lot of wind, but there's not very many other sources of energy. Some cons include that it only works if there's wind, right? It's not always going to be on, so it's not always dependable. Other cons also include the fact that each one has a low power output, so you actually have to have quite a few windmills. They're also a little ugly, some people think, and some people say they're noisy. Some people who actually live by windmills or wind turbines complain that there's this low hum, this low woo, woo, right? And that low frequency noise, they say, keeps them up at night and just makes them feel generally just kind of icky. Also, it is best for locations that are far from the city, but that's a problem because where we need the most electricity is in the city. So the places where it's high winds and open areas are not usually by the cities. So you've got to then have lots of power lines to take it back over to the cities, and that can be costly, and you lose a lot of power in the transfer as well. And the last thing is that it also has high maintenance costs. So even though it's free as far as the energy source itself is free, the wind is free, it costs quite a bit to maintain it because there's a lot of moving parts. Okay, so how do we actually calculate the amount of power produced by a windmill? What we're going to do is we're going to take again, just like all power, we take change in energy per unit time, but we say where does that energy come from? Remember, before it goes through the windmill, it was kinetic energy of the air. The air is moving, right? So what we're going to do is we are going to say that this giant chunk of air is moving through, and it has kinetic energy. So we'll say that 1/2 mv squared is the energy, where the mass is the mass of this little cylindrical chunk of of wind or of air, and that's passing through. And we're going to say, okay, how can we then calculate the mass of this, because it's air, right? That's kind of weird. Well, mass we know is density times volume, and so we're going to say, all right, so rho is the symbol for density. The volume of this times the density, we'll just substitute that in for mass. Okay, and then we no longer have mass and we just have density and volume, where again, capital V is volume, little v is velocity. Don't confuse the two. Okay, so let's calculate the volume. The volume is going to be the area of this circle right here, right? The area of this circle part, and then times the distance along the height of this cylinder. So this distance, delta x. Okay, so we'll make another quick substitution. And now we have all this information. And then we're going to say, all right, so we want to do, we see a couple of interesting patterns here. Here's delta x, here's t. We might be able to rearrange this, right? So instead of dividing everything by time, that's the same as just dividing one of them by time algebraically. And this right here is another velocity, right? So instead of velocity squared, here's another velocity. This is going to turn out to be velocity cubed. So we have here the amount of air that passes. Okay, here is that equation for power created by a windmill. Now notice that the velocity now is cubed, right? Like we said it would be. And one thing you should know about this equation is that if you just assume that this is, if you just use this equation the way it is, you're assuming that all that kinetic energy turns into electrical energy, or does whatever you're using it for. So that's a little weird, because if it all turned into kinetic energy, there would be energy or wind moving in, but it wouldn't be moving out, because after it went through, it would be stopped. And that's kind of weird. So really, whenever you're calculating power done by a windmill, you have to take this first initial amount and you have to subtract it from 1/2 a rho v cubed afterwards. So it's really a before this amount of energy, and afterwards the same amount with the velocity before and the velocity afterwards. And keep in mind, if the air is slowing down, the air will actually become more dense, because you have more molecules coming through, and they'll kind of pack up together, kind of like a traffic jam. As it slows down, right, the cars get closer together. So you'll have to have rho before, velocity before, and then you have to subtract that from the density, or rho, afterwards, and the velocity afterwards, and that would be the total actual power. Is this equation found in your data booklet? Let's see here. Yes, it is. It's found right there. It's actually the very first one, and you need to remember that the very first one on topic 8 is for windmills. This only works for windmills. So let's practice a problem. Here it is. Let's say the density of air is 1.2 kilograms per cubic meter, and the speed is going to be 8 meters per second when it hits the blade. So that's the initial speed. Now the radius of the blades, if we assume, is 1.5. The radius of the blade will actually end up being the radius of that cylindrical circle, right? So the radius of the blade, and then your circle, and the radius is, or the length of the blade is going to be the radius of the circle for your area. And we'll say that right after passing through the blades, that it slows down to only 3 meters per second, but the density increases to 1.8. So we want to calculate the power extracted by the wind. So what we're going to do is we're going to say the total energy, the kinetic energy, the mass of air has before passing through will minus the amount of energy it has afterwards. The change will be the actual amount of energy we extracted from that wind. So we're going to say power extracted is equal to power before passing through minus the power after passing through. So we're going to use the equation twice. So power extracted is equal to, again, 1/2 a rho v cubed, where this is initial, and the same thing, but final and final. We're going to plug in our numbers, because all the information is there. We just got to plug it all in, keeping in mind that the area, this is the area of the circle swept out by the blades. So the radius, again, is 1.5, and we just simply do we do pi r squared. So this right here, 2.25 is 1.5 that squared. Okay, and then we put all the information in, and we calculate about 2,000 watts is how much energy or power we have extracted from that wind. Oh, and there's my area equation.